So what we need to do is kind of identify our given information, kind of make sure we understand what we know already. So in this case, we know that BE and CE are congruent, and we know that DE and AE are congruent, and those are marked on the picture. And the other thing is we also need to kind of make sure we know what it is we're trying to prove. So in this case, we're trying to show that this segment DCD and this segment AB are equal to each other. So the bigger segments here. In this case, there's no direct relationship between them. There's no way that I could write a single equation at this moment that relates AB and CD. So this is going to be one of these situations where we need to actually write two separate equations and somehow make them be able to go together. So make them equal the same thing. Let's go ahead and read the plan and just make sure that it makes sense. So use the definition of congruent segments to write the given information in terms of lengths. So this first step is taking what we know from the givens, so these things right here, and changing them into equal instead of congruent. So when we say that BE is congruent to CE, you can also say that BE equals CE. And because this means something very slightly different than this. This means that their lengths are equal. And when we go to write equations about segments, we're talking about their lengths. So we'll want it in terms of lengths. And then we do the same thing here. DE equals AE. This is also very useful for us now because in both of these cases, we can now make substitutions. When we do end up writing some equations, we can replace BE with CE or vice versa anywhere we want, and same with these. So that can be useful to kind of start making things the same on one side of an equation. So, all right. The next thing says use the segment addition postulate to show AB is equal to CD. This step right here is not very clear in the plan. And I think this was a part where people got very, very confused when they were trying to do this on their own. The segment addition postulate is used to write an equation about a larger segment that's been broken up into smaller segments. I can't use the segment addition postulate directly to write an equation about AB equaling CD. That's just not possible. They're not part of the same segment at all. But I can use the segment addition postulate for each of them individually. So that's what I'm going to do to start things off. That AB is equal to AE plus BE. And CD is equal to DE plus CE. So I was able to write an equation about AB and an equation about CD. It's important to keep in mind what our goal is. And our goal is to show that these two things are the same, that AB and CD are actually equal to each other. And the way that we're going to do that is we're going to make the right sides match each other. So I'm going to make these sides be the same thing. And I'm going to make use of our statements right up here previously to make some substitutions. So instead of DE, I can replace it with AE because those things are equal. And instead of CE, I can replace it with BE because those things are equal. So those are two substitutions that now make these equations match each other on the right side. Since they match on the right side, then they must be equal to each other, and that's using the transitive property. So this is kind of the basic outline of my proof, and we'll write it out here in the two-column format. So we have our statements and our reasons. So first statement is the givens. You always want to restate those. I'm going to try to write this somewhat small because of space. I don't know if I have enough space right now, but so that was given. I was reading something that someone said here that AE plus EB equals AB, DE plus DC. I suppose you could do that. My question, I suppose, would be about how you you want to make the substitution. I'll talk about that in 1 second. Let me finish this one, and I think you could do that. It's how you got that equation that's at the very end that I'm confused about. Not that it's not true, but how you got it. Then we made the statement about the segments being equal. This is a pretty technical step that, that's not strictly necessary. When we know things are congruent, we do also know that they're equal, but we should do this in a formal proof. Definition of congruent segments. Then we wrote some segment addition postulate equations. So using the segment addition postulate, we wrote that AB equals AE plus BE. CD was equal to DE plus CE. Segment addition postulate. And then we made a substitution, right? We changed this second equation. So we said that CD was equal to AE plus BE by using the substitution property of equality. And now, since both of these two equations are the same on the right side, we can say that AB equals CD using the transitive property of equality. Now, technically, that's not what we were trying to prove quite. We were trying to prove congruence. So there should be a 6th step where I state that those are congruent. I'm not going to probably be that picky with this because equal segments does mean congruent segments, but technically in a formal proof, we wouldn't write that. So that's the definition of congruent segments. If two segments are equal in length, then they are congruent. So this is kind of the proof that we were looking for, at least one of the ways that you can do these proofs. There are other ways we could have done this, some other ways to create that. And I think that what you have there is okay. AE plus BED. Yeah, perhaps you could have done it that way. I am confused about that last equation. So, didn't want to do that. So this is one of a common type of proof that we're going to do at this point. Anytime you can't write an equation that directly relates the two things that you are currently trying to relate, you may have to write two separate equations and then show that those can be put together, either by making a substitution into it and kind of making that happen, or something like that. So this is going to be a fairly common type of proof that we do, where we start with two equations, change one of them, make it match up, and use the transitive property. Sometimes we can just write one equation, make a substitution into it, and then be done. But this is going to be also a fairly common thing that we do. Yeah, so I'm sorry, I'm just reading it out. I'm reading the comments here about can't use the transitive property. It's true. So here we're running into a situation where what you're saying is true. So it's not that anything that you're saying in there is not true or whatever, but I don't think that it's detailed enough there. You didn't create a situation where both of the equations were kind of identical on one side. We know that they are equal because of the substitution, since they basically have equal values on each side, and whatever one side would be, the other side would be identical. But in a really rigorous proof, you would want to fully make the substitution to make the equation for AB and the equation for CE totally match, and then put them together. It's totally accurate, and a lot of like proofs might skip the steps that I'm doing, where they just kind of say, oh, and you can see, since things are equal, that we can state that these two things are equal to one another. But it should be done a little more detailed if we can. All right, I'm going to clear this and talk about some new stuff. There's not a lot of new stuff this week. Mostly we're going to focus on trying to do some more proofs, but this is new. So we have two other types of proofs that we can do. So far what we've been doing are called two-column proofs, where we have a statement column and a reasons column, and we just kind of do one step, then the next, and the next, and the next. And it's nice. It carries all the information there, but sometimes it can be hard to follow. So there's another type of proof that I'm going to highlight, flowcharts, that we're going to be able to use. I'm going to show a paragraph proof and talk about it, but I don't encourage us to use paragraph proofs. I think they're just really hard to follow and don't really give us any additional information. Flowcharts organize the information a little bit better, a little visual to see what's connected to what, and hopefully this will make a little more sense. But so we are going to use flowcharts some, but probably not paragraph proofs, but I just want you to see that they exist. Okay, so here's our given. Angle 2 and angle 3 are complementary, and angle 1 is congruent to angle 3. If it's part of the givens, I do like to make markings on my picture to indicate that. So since it wasn't marked there, prove angle 1 and 2 are complementary. All right. So here's the flowchart proof of this problem. You can see it's not just like a T-chart with statements and reasons. The statements and the reasons are kind of grouped together. Like, so this was a given statement, so it just kind of goes with that. And we have these bubbles with arrows, and the arrows are really where a flowchart conveys information better than a two-column proof. When you're doing a two-column proof, you're not necessarily showing me where, when you make a new statement, you're not showing me where that new statement came from. You kind of have to look up at the previous steps to see, was this related to something that was said before? And it can be difficult to follow. Whereas a flowchart proof has these arrows. It shows me exactly what statement I used previously to make this new statement. So when we have this given information that angle 2 and angle 3 are complementary, I can see that that is directly related by this arrow to this equation, that angle 2, the measure of angle 2 plus the measure of angle 3 is equal to 90. And this is the power and the usefulness of a flowchart proof. We are seeing where the ideas are connecting, how we're taking these separate given informations and combining them down into our final conclusion. I also like to think about flowchart proofs in terms of kind of layers. The top layer, or the first layer, is anything that is given to us or anything that we can infer from the picture. So givens are obvious, they are stated for us. But some things that we might infer from the picture would be like if we had a segment like this and we were writing a segment addition postulate equation. That would go up here because the picture is actually sort of like another piece of given information. you have your given statements, but then you also have your picture, and it is technically part of the given information. And some things we might be able to tell from that. So if we had a picture like this, and we use the segment addition postulate to say something like this, now the reason we would give is a segment addition postulate, but technically it's from the given picture that we're actually getting it. And so it would kind of go up here in this first layer of given and things that come from the picture. All right, that's not what I meant to do. All right, then we have a second layer here where we are taking those given information things and making, what do they mean? So this right here is my second layer, where I've taken my given and I wrote an equation. This is what it means to be complementary. They add together to be 90. Or these two angles are congruent, which means that their measurements are equal. Definition of congruent angles. So we've taken our given information and we said, all right, what does that tell us? What can we do with that given information? And then this right here, where everything starts to converge together, this is the key to the proof. And this is the place where people have a very hard time with proofs in general. They can start with the givens and they can maybe say a couple things about that, but how do they bring it all together into something that ends up leading us to the conclusion? And this is where the proof really comes together. So in this case, these two angles add to 90, and angle 1 and 3 are congruent, so they can replace angle 3 with angle 1. They made a substitution. They took this equation, which was based on the given, and this equality here to make a substitution. So that's great, because this right here is basically what we're trying to prove, that angle 2 and 1 are complementary, and this equation shows they add to 90. Therefore, we have it right here. This is our conclusion. So this step right here, where we start bringing things together, this is the piece that people get confused with no matter what type of proof we're doing. Whether we're doing a 2-column proof or whether we're doing a flow chart like this, is how do I take all this stuff together? And sometimes that comes in the form of making a substitution like this, and sometimes it comes in the form of taking two equations and putting them together by using the transitive property. So we have to be kind of paying attention to how we can start bringing our separate ideas, our separate branches into one. We're going to create a flowchart proof here in just a second. I just want to show this. Again, we will be using flowcharts. I recommend using flowcharts because they convey a lot more information than your regular 2-column proof. Those arrows really show how our ideas are connecting. Let me clear this. Paragraph proof. This is an example of a paragraph proof. The basic idea of a paragraph proof is it doesn't really convey any more information than a 2-column proof. It just takes each line of our 2-column proof and turns them into a sentence. So for instance, we are given that Wx equals Yz. This is just the first line of a 2-column proof. This is my statement. This is my reason. And there's some words in there connecting it together into a sentence. Same idea. Our second line is, well, here's the reason, segment addition postulate, and then here are the two equations that we write as a result. It essentially takes each line of a 2-column proof and turns those into sentences. Now, unlike a flowchart proof, a paragraph proof does not necessarily give us any extra information. We can add some extra information in there, and this sentence right here does do that. It kind of tells a little bit more than what a 2-column proof does, but usually they don't. They just kind of take each line of a 2-column proof and just kind of add some words in there to make it a sentence. So we're not really going to be using paragraph proofs. I think with paragraph proofs, students often get confused in that they don't write all of the things out in their paragraph proof that they would write out in a 2-column proof, because you're used to writing down arguments for other classes where you don't necessarily have to write down all these little minute details. A lot of things can be inferred just by what you say. So, you know, people tend to leave out details when they're doing a paragraph proof. So that's why I don't really encourage it. And they're just a little bit harder to follow. They don't organize quite as well as a 2-column or a flowchart. But they exist, and if you take higher level math classes, a lot of times many of the proofs are done in paragraph form rather than a 2-column format or something else. And they'll be paragraphs provided with drawings and graphs and different things like that. So, you know, it's important to know they exist, but we won't be using them very much. Okay. I already said all this. If we are given a problem and you're supposed to do a proof, you can choose any of these formats, though I do encourage 2-column and flowchart. And those are the ones that I'll be using. Okay, so let's, nope, this is the one that we already looked at. Let's do this one right here. Okay, so let's create a flowchart proof. Hopefully we'll have enough space to do this. I think that we will. So it is given that angle 2 and angle 4 are supplementary. Okay. And we have a picture, so that's also given to us. And our goal is to prove that angle 2 and angle 3 are equal. Okay. So when I'm doing a flowchart proof, I like to either work from top down, like the example was, or from the left to the right. My preference is top down, but you know, based on space, you might want to work left to right or something. But I'm going to go top down with this, and I start with my first layer. And the easiest thing is the given. So angle 2 and angle 4 are supplementary. And that is given. And I will put a box around that. Okay. And also included in my top layer are anything that I can infer from the picture. Now, something that I can infer from the picture are linear pairs. I can see in this picture I have 2 linear pairs. So I will be also including that in my top layer of like the given information. So I will say angle 1 and angle 2 are supplementary. And I will say that angle 3 and angle 4 are supplementary. The reason that I'm going to give for that, I could say a couple different ways. I'm just going to say they are a linear pair. Technically, this is also called the linear pair theorem. Linear pair theorem. It is a theorem that we proved a couple days ago. So we're going to go ahead and use it as a reason. I'll put boxes around this. For flowchart proofs, which is a little different than 2-column proofs, every fact that I make, I'm going to give it its own box because it might go to a different thing. And I don't want to get confused and have multiple facts in the same box that end up going into different places. All right, let's do a new color to do my next layer. All of these say that I have supplementary angles, right? So we want to keep in mind where we're going. We're trying to show 2 and 3 are equal. So I need an equation that has both angle 2 and angle 3 in it. This one would have 2 and 4. This one would have 1 and 2. This one would have 3 and 4. Okay, let's see here. So all of these give me one particular type of an equation. They say the measurement of angle 2 plus measurement of angle 4 equals 180. This one says the measurement of angle 1 plus the measurement of angle 2 equals 180. This one shows the measurement of angle 3 plus the measurement of angle 4 equals 180. And those are all just the definition of supplementary angles. If I know angles are supplementary, I know they add up to be 180. I was trying to copy that, but that's okay. I'll just draw a box around them. I'm using the same reason for all of these. I don't feel like writing out definition of supplementary angles 3 times. We'll just assume we know that, and I don't know that I have the space. And I need some arrows. The arrows are the point of a flowchart proof. Shows us what ideas are connected. So these given statements or statements from the picture all came from or led me to this. All right. Since they all equal 180, any of these 3 things would be equal to each other. What can we do here? Again, trying to keep in mind, we want to show that angle 2 and angle 3 are the same. Angle 2 and angle 4 are supplementary. All right, let's do this. Let's put together the first 2 and see what happens. I don't know my plan yet. That's why it seems a little bit odd, but I'm going to put together these 2. Since they both equal 180, let's just see here. So measurement of angle 2 plus the measurement of angle 4 would have to equal the measurement of angle 1 plus the measurement of angle 2. They both equal 180, so they would have to be equal to each other. This is the transitive property. And that came from here and here. We put those 2 equations together to make this new equation. Well, it's pretty easy to see that I have angle 2 on both sides here. So if I subtract angle 2 from both sides, that leaves me with measurement of angle 4 equals measurement of angle 1 using the subtraction property. Right? Again, I don't know entirely if this is leading us the right way yet. So we're still just kind of working it out. So now that means that I can substitute angle 1 and 4 anywhere I want. But that's not what we were going for here. We were trying to show 2 and 3 were equal. So maybe that was not as helpful as I had anticipated.
You can use one of them as a substitution in one of the properties that were led, one of those, yeah, and then subtract it and get that the measure of 2 equals the measure of 3.
Yeah, and I like that. I think that's really good. I think that I could do that, but I will eventually. But I think even better in terms of like fewer steps, instead of putting those 2 together, what if I put together this one, and this one. So that's going to give me, oop, I don't want to draw an arrow. That would give me measurement of angle 2 plus measurement of angle 4 equals measurement of angle 3 plus the measurement of angle 4. And now, since I'm trying to show that 2 and 3 are equal, now if I subtract 4 from both of those, I'm going to just end up with measurement of angle 2 equals measurement of angle 3. And so that was, again, the transitive property of equality. And then when we subtract angle 4 on both sides, we end up with just measurement of angle 2 equals the measurement of angle 3. And that was the subtraction property of equality. I missed a box there. So I was hoping to show a few things here. One, how to create a flowchart proof. But the second thing was, you don't necessarily need to know the exact path that you're going there. Sometimes you start making a proof and you realize it got me something, like we ended up with like angle 1 was equal to angle 4. That was a result, but it just wasn't quite what we wanted. So I had to go back and try something else. I went back and said, okay, putting those two together didn't really help me. Maybe let's try to put a couple others together and see if we can get what we're looking for. We have to do that with proofs. We're going to have to kind of make a rough draft and leave things out. In fact, I don't want to leave you. It's our time to go right now. So if you got to go, that's fine. But in fact, this didn't lead us anywhere. I didn't even make use of these ideas at all. I didn't even have to have them in the proof, right? They didn't lead anywhere towards my final result. I just needed this one and this one. But there you go. That's an example of a flowchart proof. We'll go over a lot more examples tomorrow. Again, I just want to spend this week kind of doing more geometric proofs. Homework's posted on the classroom page. It's a worksheet, a little different. Bye, guys.